Good afternoon, everyone. Hello again for our fourth webinar within the Connect to Learning Series 3. Today we have a talk about facts and myths about dyslexia by Rebecca Gordon. I would like to remind you that this initiative is a collaboration among the Institute of Education at UCL, the Faculty of Education at the University of Malta, and also Educational Neuroscience Hub. Together, we're bringing to you 7 webinars on this area. We're in the 4th one. As we do, usually we'll later share a link so that we can record your attendance. And eventually, if you attend these live webinars, if you attend 5 of these 7 live webinars, you'll be entitled to a certificate, which we will send at the end of this series. We would also like to encourage you to post any questions or comments in the Q&A facility, so that after Rebecca's talk, we can take up your questions and we'll invite Rebecca to answer as many questions as possible. I will leave the word to Erica and eventually to Michelle to introduce Rebecca and today's topic. Up to you.
Thank you. Thank you, Rebecca, for being here. I believe a teacher's ability to understand how the brain works and how they can influence a student's learning should be at the very heart of education. Therefore, the aim of this collaboration between the Faculty of Education, the Education Neuroscience Hub, and the Center of Education and Neuroscience is to create awareness and a better understanding of the development of the brain within the context of teaching and learning. Teachers who use a scientifically informed approach to evaluate educational assertions will be able to help their pupils learn more effectively. And more importantly, these webinars also aim to create a bridge, a common language between science researchers and practitioners, as well as parents, enhancing evidence-based strategies which are more likely to succeed with today's students. Thank you. Hope you enjoyed the talk. Michelle, on to you.
Yes, I'm going to introduce Professor Rebecca Gordon. She's an associate professor and director of the Motor Executive Cognitive Interaction Lab at UCL Institute of Education. She's a cognitive psychologist who is a chartered member and associate fellow of the British Psychological Society and a member of the Management Committee for the Center for Education and Neuroscience. She also runs the ESRC accredited MSc in Developmental and Educational Psychology at UCL. Her research focuses on memory and executive function as it relates to academic outcomes such as reading and mathematics. She's also interested in the relationships between executive functions and dyslexia in children and adults. I'm going to briefly introduce this particular session. In this session, Rebecca Gordon will discuss what we know about dyslexia, including the brain architecture involved in learning to read and what happens when things go wrong. Considering this, we will also look at many of the myths surrounding this condition and how people with dyslexia struggle with abilities other than reading and spelling. And without further ado, I now leave the floor to Professor Gordon to tell us more about this particular condition.
Thank you, Michelle and Erica and James. First, I haven't yet reached full professor. I'm still Dr. Gordon, but I appreciate being called Professor Gordon, albeit briefly. Thank you for coming to this talk about the facts and myths about dyslexia. As Michelle said, I am a cognitive psychologist and I look mainly at executive function / working memory, but as they relate to other conditions and abilities such as reading and dyslexia. So the caveat I normally give when I give talks such as these is that I'm not an interventions researcher. So I know a little bit about what types of interventions work, but I don't know in great detail because I don't conduct interventions research. I don't know about that in great detail. So I'm just saying that up front so that when we get to questions, I don't disappoint you too much when I say, oh, I don't know about that. That hopefully won't happen too often. Right, so let's have a look at what we're going to talk about today. So first, we're going to look at what dyslexia actually is. and then what reading is, and you'll see what I mean by that when we get to it. We'll then take a look at what we know about the dyslexic brain. There is a whole lot we could discuss, and we could do a whole series of seminars on that, but we'll just stick to the basics. And then we're going to look at whether these differences in brain structures, brain architecture in people with dyslexia compared to those who do not have dyslexia, whether they are a cause or a consequence of this condition. Then we'll look at beyond reading. So looking at the broader cognitive deficits that people with dyslexia experience. We'll touch on neuromyths and why it's important to understand that they are neuromyths, and then look at things that you should know about dyslexia. So things that are neurofacts, if you like. Right, so dyslexia. First of all, what is dyslexia? Well, the word itself means difficulty with reading. So difficulty, or meaning difficulty or impairment, and lexia, which is understanding of words. And people who are diagnosed with dyslexia should have difficulty with reading that is not explained by their lack of education or broader IQ problems or even emotional problems. It should be an isolated atypicality. It is also related to other literacy deficits. So people who have dyslexia don't just have problems with reading, but also with spelling and also with writing. And there are, as I said, brain differences in people with dyslexia compared to typical readers. It affects approximately 5 to 10% of the population, but we don't know for sure how many people are affected. It's probably a lot more, and there are a number of reasons for that. Difficulty in diagnosis, the fact that dyslexia is most likely a spectrum, so people who don't present with extreme difficulties might not seek diagnosis, and obviously in different countries it manifests in different ways, and we can look at that as well. So as I said, it produces anything from mild to very severe problems with reading. And another thing to note is that it is highly hereditary. So there is a genetic aspect to it. So if you have parents with dyslexia, you are more likely to have then a child with dyslexia. So why would it be important to look at this condition? Well, there's a lot of evidence that obviously it's related to poorer academic outcomes, so poorer educational outcomes, because reading underpins most of what we do in schools. It can also result in behavior problems because of the frustration linked to it. So frustration in not being able to develop these reading skills that a child will see their peers being able to do with relative ease. But also other frustrations related to the broader cognitive deficits that we'll get to. And then, of course, problems with self-esteem, feeling that I must be stupid, why can't I do this, or my friends can do it. But as children with dyslexia grow up, even if through remediation they learn to read and spell at normal levels, they still do have poorer academic outcomes based on performing more poorly in higher education settings and also in their career progression. And these are due to these broader deficits, which we'll talk about later on. So why reading? This is the fascinating part about dyslexia. So reading is not an evolutionary construct. When you think about language, this is an innate biological process that we have evolved to have. But reading isn't. It's a human invention. It's about 3,000 years old. I think I saw something in the news just last week where there was a lice comb, you know, for hair lice, that had a sentence written on it. And that was 3,800 years old. So maybe it's a little bit older, but it's certainly not old enough to be an evolutionary construct. In terms of widespread literacy, so in developed countries, pretty much everybody being able to read once they reach 6 or 7 years of age, that's only existed in about the last 100 years. 150 years ago, illiteracy was quite common. So the question is, how can a neurodevelopmental atypicality relate to reading, relate to this invented construct? And the fact is that it isn't. It manifests as a reading disability, but the impairment or atypicality or disorder or whatever term you choose to use is linked to something else. So it's to do with speech sound formation. So this is not about language. This is different to language production. This is about the sounds you make and them being matched to sound components of a word to a letter. So this is something that we have to develop in a very artificial way because it is not innate. So for example, if you look at the English word bed, and I could say to you, okay, bed is made up of 3 letters, a B, an E, and a D, and the sounds they make are B, E, D. And so B, E, D spells bed, but it doesn't. If you think about it, no matter how quickly you say it and how much you try and mush those letter sounds together, it doesn't actually become bed. So it's then it just becomes a nonsense thing. So in a very artificial way, we have to invest in a belief that b and e and d create the word red. But people with dyslexia find it very difficult to sort of get on board with this contrived mechanism. Let me just have a sip of water. And the thing is, that once we start to learn to read, once we start to understand letter sounds and then groups of letter sounds and then groups becoming words, it's very, very, very rapid. And children who are able to do this acquire reading quite quickly. But as I've said, unlike something like language, which is innate, this is very much contrived. So the majority of people are learning to do something which our brains aren't actually designed to do. So why do children with dyslexia find this so difficult? So we use speech sounds all the time. So for example, back in 2019, somebody came to work in our department, a colleague of mine who I'd also consider a friend, and his surname, this is Greek, and his surname is Sideropoulos. Now, the first time I saw his surname, I had not seen that particular surname before. I hadn't seen that word before. It was a novel word, but I was able very quickly to work out how to pronounce it. So I had SID, so that's Sid. Okay, Sida. Okay, could be cider, but those combinations tend to be Sida because I know words like consider. And then I know that OP is op, and then pool is quite a common pronunciation. So I can, and then I can put them together as Sideropoulos. And I say it to myself, 2, maybe 3 times, and I've got it. So I'm combining these common letter combinations to create sounds, and then I create the word. This sort of thing, people with dyslexia struggle with very much because it just doesn't make sense to them. And we'll get onto that in a bit later. But we don't just use these phonological skills to learn to read. So we don't just do this phoneme to grapheme mapping where a symbol like A, the first letter of the first sentence here, and is A. What we also do is we recognize words as a whole image. And we especially use this for irregular words, of course. So in the English language, we're wonderful for having these irregular words. There's loads of them in the English language, but you look at these words here like wait, debt, yacht, aisle, answer, choir. You could not do phoneme mapping to work out how to pronounce them. So if you take yacht, for example, which is a great one, so ya-ch-t, it never becomes yacht. So when we learn to read, we also learn to recognize that whole shape as the word yacht, which is something else that people with dyslexia struggle to do. And we'll get into that when we start looking at the areas of the brain and the neurobiological explanations for dyslexia. So what I'm basically saying here is that the process, there's more than one process involved in reading, and that there's actually a very complex neural network, but obviously I'm going to keep it quite simple because I don't have time to give you a whole lecture on it. But you have the orthography, so you have the written word, so we'll stick with the example bed, and then you have the phonology. So this is not, what I've done here is I haven't broken it into b-ed. We've moved on to the whole word sound now. So we have the orthography, the written word bed, and knowing that that written word, that shape of a B and an E and D together, creating an image, makes the sound bed. And then we have the semantic knowledge that this is what we're talking about. We're talking about this bed here. So there's these interrelated processes. Now, in terms of brain mechanisms, we have, I just need to move part of my screen across. So, like I said, there are complex neurobiological neural connections that are involved in reading. So it's not as simple as this, but these are the key areas involved in reading. We have the left inferior frontal gyrus, so the frontal lobes here at the front of the brain, and the lower part, and then the left temporoparietal cortex, so here on the left side, which I'll get to in a minute, but is also implicated in language. And then we have the left inferotemporal cortex, and this is the part of the brain that is about the orthography, so what the written word looks like. So those two first areas, the left inferior frontal gyrus and the temporal parietal cortex, they activate when we're undertaking phonological assembly for unknown words. So my example before of my friend Sideropoulos, that's his surname, Vasilis Sideropoulos, you would use these areas of the brain to combine those components of the word to create this novel word, to be able to produce it. And then you would access meaning. So in this, obviously, is my friend and colleague Vasilis, but if it was bed, it would be knowing what a bed is, etc. Then this area down the bottom, the left inferotemporal cortex, that is the recognition of the word. Now let me just go on to give you a little bit more detail about this. So like I said, this frontal area calculates the pronunciation for production. So once again, I'm not talking about language production. I'm talking about when you read, you produce the words, but you don't say them. But you might if you're reading out loud, but quite often we're not actually reading out loud, but you still produce the word. So you look at the image, or you combine the phonological components, and you produce the word. So the frontal area is activated when that is being undertaken. And then this temporoparietal cortex, so this left side of the brain here, becomes used for reading as we learn to read. So it is an area of the brain that in terms of evolution is for language, but we then start to use it also for reading, because like I said, even if you're not reading out loud, you're still producing these words. So there's a production of the sound of these words. You kind of hear them in your head, if you like. And then this area down the bottom in the inferior temporal cortex, this is the really interesting area because it's the area of the brain that we use for image recognition. So the recognition of faces and other images, but we have stolen it for reading. So as children learn to read, there are physical changes in this area of the brain where we're kind of going, okay, so we're going to hijack this area of the brain and we're going to use this for reading so we can recognize all those frequently appearing words. And so in combination, these processes are used to read, and they rapidly become quite automated as we go through primary school and secondary school and become And then by adulthood, if you're a typical reader, they are very, very much automated. So all this is to say that there are I will get later on to the differences in the brain, but compared to dyslexics and people without dyslexia, but those three areas of the brain, you do see different patterns of activity in people with dyslexia compared to people without dyslexia. But it's difficult to say whether these brain differences are a cause or a consequence of dyslexia. So excuse me, just having some water. Do, for example, children with dyslexia that have a reduced activation in this area of the, I thought I could go backwards, but I can't, sorry, that have reduced activation in these two areas of the brain, the temporal parietal cortex and inferotemporal cortex. Do those brain differences result in these children having difficulty in reading, or do children who have difficulty in reading end up having these brain differences? Okay, so quite often when we do studies of people with dyslexia, they've had several years of altered reading experience, often reduced reading experience. So if a child has dyslexia, they might read less often or be exposed to words less often. So it would make sense if they have reduced activation in, for example, the recognition area of the brain, because they're exposed to fewer words. But also, we are very good as human beings at developing compensatory strategies. If we can't do something very well, we'll develop a strategy to enhance that ability. A good example is short-term memory. So everybody's short-term memory is very limited, but we do things to enhance our short-term memory. If you're trying to remember a phone number, you will repeat it. It's usually subvocally, just inside your head, or maybe just under your breath, 32457, 32457, to enhance your short-term memory. Well, we do that for a lot of cognitive processes. And if somebody has struggled to read for a number of years, they may, I'm not saying this is definitely the case, but it might be the case that their compensatory strategies have led to alterations in the reading networks, which is why they are different to typical readers, why their brain activation in these areas of the brain is different to typical readers. So I just want to get, there are several, like I said, we could do a whole series on explanations for dyslexia, but I just want to go through a couple just to give you an idea of how research is done, well, not in detail, but how explanations for dyslexia are undertaken in terms of neuroimaging studies. So this is one hypothesis, the magnocellular hypothesis. And this is this refers to atypicalities in very specific neurons in the visual system, the magnocellular neurons. And these are very large neurons. They're the largest neurons we have. And because they're so large, they process information really quickly. And they're also associated with motion perception. Now, you might think, what's reading got to do with motion, but it's to do with your eye's ability to track words. So you can imagine when you're reading, if you read this top sentence here, post-mortem evidence, which I'll get to in a minute, etc., even though your eyes are doing the movement, you're actually tracking something that is moving, if you see what I mean. So this was based on post-mortem evidence, so evidence from people's brains after they died, people who'd had dyslexia, that they had smaller magnocellular neurons in the visual system compared to people that did not have dyslexia. So that's how this hypothesis evolved. And studies were done looking at this and continue to be undertaken, actually. But a very recent review of dyslexic theory has looked at this, and the activation in dyslexic children, if you take some, quite often when you do research with children with dyslexia, you will compare them to a control group of ability matched children. You normally have an age match if you want to look at reading ability, but then an ability matched if you want to look at other aspects that might be connected to their reading ability. So if you have a 10-year-old child who has dyslexia and their reading ability level is of a 6-year-old, you would compare them to a 6-year-old that has typical reading levels. And what researchers found, neuroimaging researchers found, is that activation in this area of the visual system where the magnocellular neurons activate, it's in dyslexic children, it's equivalent to ability matched children, which you wouldn't expect to see if the activation was the cause of the dyslexia. What it suggests is that a lack of activation is equal to the level of reading experience of the person. So a child who is 6 will have an activation level that's comparable with the reading age of a 6-year-old. A 10-year-old will have the activation level. A 10-year-old with dyslexia who has a reading age of 6 will have the activation level that's comparable to a 6-year-old. And this does make sense when you look at reading remediation for people with dyslexia, because what this does, this reading remediation, where you spend a lot of time getting people with dyslexia to practice the phonological mapping phonemes to graphemes, and also irregular spelt words, familiarity with irregular spelt words. What happens is that the reading remediation enhances activation in the dyslexic children. So again, this points to the level of activation being equal to the level of reading experience, which would suggest that this area, these magnocellular neurons, the atypicalities you see there, are a consequence of dyslexia rather than a cause. It's also what have I said here? No brain structure differences between dyslexic and ability matched children. I think I've pretty much covered that. So yes, so that's what the evidence, though I know that people would disagree, and I think that John Stein, who would disagree with this, but this is the more recent research and meta-analysis and reviews are pointing towards this more likely being a consequence than a cause. So let's have a look at the double deficit hypothesis. So what this says is that the impairment that children and adults with dyslexia have related to reading is a deficit in, representing phonetic sounds, and a deficit in access to those sounds. So the ability to map to the sound to the letter and also have an access to those sounds. And these children are tested on these abilities in some very similar ways, like variation on a theme, but very similar ways. So for the access to the sounds, children are normally tested using a rapid access naming task. So it might be name as many types of fruit as you can, and you record the speed and accuracy and the length of list that children can access that information. And you can do it with smaller units, not just larger things like whole words. You can do it with sounds as well, letter sounds as well. And then you have the phonetic sound. So that's looking at a group of letters and being able to match a sound to a group of letters. And the neuroimaging evidence is that there is a distinction between rapid access to sounds and also the phonological ability related to those sounds. So this phonological decoding of being able to say what sound different components of a word say, what sound individual components of a word map to or make, this is related to the left area of the cortex related to language, and then the naming speed, so the access to those sounds, is related to the occipital, temporal and parietal and frontal lobes. So this is more like a whole brain thing. So activation in the left inferior parietal lobe is associated with phonological awareness. So that's understanding what those components of words, the sounds they make. And then we have activation in the right cerebellar lobe, and that's a whole area to look at, which I don't think we're going to look at today, is linked to rapid access naming. So there is neuroimaging support for this double deficit hypothesis. And there is certainly in behavioral studies, so studies that don't use neuroimaging, very, very large scale studies, so studies with a lot of, thousands of participants, that there are children and adults who they have dyslexia, but there are 3 different groups that you can identify. One are those that don't have a problem with breaking down a word into the individual sounds to work out what that word sounds like, or being able to read that word, but have a real problem with irregularly spelt words like yacht. And then you have other people with dyslexia who have no problem with irregularly spelt words, but do have real problem is breaking down a word into the separate sounds. And then you have groups of people have both those deficits. So there is some evidence for this, but again, whether this is a consequence of having dyslexia and there's something more underlying going on, or whether this is a cause for the dyslexia is still, well, some people would say it's definite, other people would say the jury's that it isn't definite, so the jury's still out on that one. Right, so yes, so linking back to whether this actually makes sense in terms of dyslexia. Well, dyslexic children do show reduced prefrontal activation during auditory phonological tasks. So this is the production of those sounds, but they don't have any difference in the temporal lobe activation compared to age and ability matched children. So these are the children, the age match, like I say, getting a 6-year-old to match the 10-year-old. So they don't, I can just go back, they don't have a difference in this area of the brain, so the temporal area here. So what this would suggest is that they know the sounds, they just have difficulty accessing them, is possibly the case. But like I said, jury's still out, but I'm just giving you an idea of the type of research that is done and how complex dyslexia is. So yes, that's what I'm saying here. Basically, I could go on, but what I'm saying is that reading involves very, very complicated bidirectional processes. So our brain is not designed to read. It didn't evolve to read. It's something artificial that we have to acquire. And people with dyslexia have trouble acquiring these processes. And there is evidence that they have problems breaking a word into small sounds and mapping them to letters. And that they also do not understand the relationship between the sound and the letters written is not clear to them. They don't understand what, and when you think about it, you look at the letter P, it's just a shape. Why does that make the letter P? And it's much more prevalent in English-speaking countries. So here is the wonderful OUGH sound that we seem to love in the English language, which has so many different pronunciations. So we have what is called an opaque orthography in the UK, well, in English-speaking countries, sorry. So you can look at these words that all have OUGH, but they are pronounced plough, rough, dough, through, thorough, fought, cough. So they all have different sounds. This is probably a good example to think about what it might be like to have dyslexia, because you just can't see the relationship between those shapes on the page and the actual sound they make, unless you're able to read the shape of that word and just know the sound it makes. In non-alphabet languages, so like Cantonese, Mandarin, etc., dyslexia doesn't manifest in the same way. We know it exists because there's a number of other tests that we can do to see whether these speech sound impairments exist, but it doesn't manifest in reading because we don't have this, they don't have this alphabet-based language. And it's also less prevalent in transparent alphabet-based languages such as Italian and Spanish, where there's far fewer irregularities. And so these are some great irregularities again from the English language. So words like fuchsia and sui and cologne, beauty, that's a good one. all like women. That's a great one because it's such a common word and we say it all the time and you just say the word women, but you know that would be W-I-N-I-N, but we never say women, do we? So that's just another good example. There's also if you rank languages in terms of their from transparent to opaque, and you test people on reading accuracy and speed, the more opaque the language or the more inconsistencies there are in the language, then the more time it takes to produce the words, and also more errors are made. So going here from Finnish through to English, and also the more inconsistency there is in the writing system, so the more opaque the language is, the longer the developmental times, the developmental trajectory times are for basic reading skills for children. So all of that is to say, like I said, it's a complex process. It manifests in reading, but there are other deficits. There is a lot of research that shows that people with dyslexia have problems with short-term memory and working memory. So the ability to hold small pieces of information in mind for short periods of time. And working memory, if you had to concurrently process some other information, it's even more difficult. Prospective memory, remembering to remember. So remembering I've got to post that letter on the way home, or buy some more milk on the way home, etc. More failures, day-to-day failures in people with dyslexia compared to people without dyslexia. They also perform more poorly in planning tasks. So planning the order and timing which things need to be done, and also the organization of those tasks. So prioritizing things, making sure that things are in a logical sequence or in logical categories. So what this suggests is if you look at it in evolutionary terms, it's an impairment in this ability to adapt to environmental demands and predict what needs to be done. That's what the evidence suggests, but it's fairly early days, and there's some work, but work now is only just starting to pull all this together. What this implicates is impairments in the frontal lobes, so the areas of and I'm not talking about the reading networks now, I'm talking about the broader cognitive networks. So impairment in the frontal lobes, which would explain problems with prospective memory, short-term memory, working memory, and these executive skills such as planning and organization, but also the cerebellum, because in terms of organization, there's this, in terms of evolution, there is this connection between, and many other areas of the brain, but simplifying it, from the connection from the cerebellum through to the prefrontal cortex, there's this bidirectional relationship, which allows us to identify environmental changes in our environment, predict what needs to be done, and adapt our behavior in order to meet those demands. And then for this to actually become an automatic ability, so that we don't have to relearn it every time something different happens. So there's suggestions, it's early days, that it could possibly be this network. Whether this is a cause or a consequence, there seems to be an impairment in this network. And this is lifelong. This leads to lifelong deficits, which I'm going to talk about, I think, on the next slide. Yeah, so it's the reason it's important to understand these broader deficits is the impact of these can be lifelong. So children with dyslexia can go through remediation, through interventions, and learn to read and spell at typical levels. They might not be like excellent readers, but they will be adequate readers. But obviously in school, having dyslexia leads to poorer educational outcomes if reasonable adjustments are not put in place, because reading underpins everything. And there's those other knock-on effects such as frustration and self-esteem. But they also lead to poorer outcomes in terms of further and higher education, career progression, and obviously economic outcomes. And there are qualitative studies that have shown that adults with dyslexia are less likely are reluctant to report their dyslexia in the workplace because they're worried about the impact it might have on how they are seen and their career prospects and you know the type of responsibilities they'll be given. I think, you know, they're basically worried that people will think they're stupid and not capable. So it's problematic. But early interventions, and talking here about broader deficits, can introduce compensatory strategies at an earlier age. Now, I talked earlier about, you know, we all do a lot of things automatically to boost our cognitive ability, such as verbal rehearsal to try and remember something. If you can introduce these compensatory strategies early, children can start to use them and, for want of a better word, internalize them, and the use of those strategies can be lifelong. So rather than just giving up and going, well, I just must be stupid, or I can't do it, what's the point? They actually learn how to help themselves and aid their, you know, working memory, their organization skills, etc. And the benefits of that can be lifelong. So like I said, this research is in its infancy. It does tend to be more with adults, but there's a lot of research. We know that there are these executive deficits and prospective memory deficits in adults with, sorry, my dogs are barking, in adults with dyslexia. We also know that prospective memory and executive function are important in children, but the research specifically looking at prospective memory in children with dyslexia, there's really nothing there. I think I found one study. So that is a gap, and it's something that does need to be looked at. Right, so yes, on to neuromyths. I'm just keeping an eye on the time. I'm going to talk you through these briefly and then tell you why I think it's important to bring them up. It's not about going, ha, 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 I can't believe people believe this. So one is visual stress. Now, yes, children with dyslexia and adults with dyslexia will experience visual stress, but so do other people who are typically developing readers. There are a number of reasons for it. I don't want to, there's not time to go into it all today. It's also not my area of expertise. Sorry, my dog is barking at me. But the idea that dyslexia is purely caused by visual stress, and you can use these color overlays and that will help children with dyslexia or adults with dyslexia, problem solved, off we go, is incorrect. There is not evidence. In fact, meta-analysis study show that the evidence for this idea of visual stress that can be alleviated by these color overlays is really negligible. There's really not much there. And well, actually, I'll get onto that in a second. The other one is right brain dominance, and I'll talk about that when I get to that slide because I'm getting ahead of myself. The other is letter reversal, and the other is creativity. So let's look at the first one, which I've really briefly touched on anyway. So visual stress, it stems from the original diagnosis of word blindness in the late 19th century. There isn't evidence to support it. Like I said, children with dyslexia have visual function and health the same as their typically developing peers. There's no evidence that they have any visual function or health problems. Like I said, it's something that you find in typically developing children and adults too. There is some research, though it's very, very, there's not a great deal. And because of the problems with things like publication bias, we don't know how many studies there are that show the opposite of this, that adults with visual stress are more likely to show improvements using overlays if they also have dyslexia. So we're not saying people with dyslexia always have visual stress, and we're not saying that color overlays always alleviate visual stress. We just say that there's slight indication, a slight effect of adults with dyslexia showing more likely to show improvements, not always, but more likely to show improvements if they also have dyslexia. But you have to consider that it may be possibly a placebo. So I'm not saying it magically enables them to read, but they might get a sense that they are able to read better or they have less visual stress. So again, the evidence is thin there. So this is a good one, letter reversal. So letter reversal is often said to be, oh, letter reversal, that's a sign, you want to watch that, that's a sign of dyslexia. Well, there's no evidence that this is specific to dyslexia, and it's actually a normal part of child development. Children, whether they're dyslexic or not, can reverse letters. Also, children who have dyslexia may never do this. So it's problematic to assume that this is a definite sign. The reason children do it is when they first start to interact with objects, those objects, you can, whichever way you turn them, they're still the thing they were. So if you think about the cube, or, you know, I've got a box here, whichever way I turn this, it's still a box. But that doesn't happen with letters. And this, I like this because what it highlights is how sort of abstract this idea of letters meaning certain sounds is. So if you look at this chair and a B, so they're one position, and the B is B and the chair is a chair. And then you go to the next one, you reverse it, all of a sudden that becomes D, the chair is still a chair. And then you flip it on the horizontal, sorry. No, on the vertical, or whatever. And it's now P, but the chair is still a chair. And then you go to Q, so it's now K, but the chair is still a chair. So it's quite normal for children to struggle with this idea that you can't just write the stick with a loop in any way you want, because it will actually completely change the sound of that letter. So a continued reversal through to later than peers may indicate a delay, but this is not like a definite symptom, because otherwise most children we would identify as at risk of dyslexia. Right brain dominance. So this came from lateralization studies that used to be done, that there was this idea that one side of the brain was, that the left side was sort of logical and the right side was about creativity. And so if children with dyslexia have a problem with language-based skills such as reading, then it's because they're right brain dominant. So it means, and we'll get onto this, they have more creativity, etc. Again, no reliable evidence for this as a cause. The questionnaire studies that are done are problematic because they ask questions like, you know, where you have to rate on a scale of 1 to 10 or whatever, 1 to 5, whether you agree or disagree. They might say, they might have a left brain question. I find it easy to think of synonyms for words. That's all language sort of stuff. And then a right brain question, I have a good sense of direction. So that's kind of like the spatial idea. And then what they do is they subtract the right brain scores from the left brain scores to create this index of hemisphericity. But it's problematic because there is a lot of supposition as to what constitutes right brain thinking. And you know, any results in this study could be something as simple as a deficit in rapid access naming that we talked about earlier. So there are studies out there that say, oh, look, left brain, right brain, but they are not very well designed. And there's much more evidence to say that this is not a cause of dyslexia. Right, what's the next one is creativity. Okay, so once again, now this is a nice idea, and there are loads of examples, aren't there, of people, film directors and architects and painters and actors, etc., who have dyslexia. And there's this idea that, oh, people with dyslexia are more creative. Now, I'm not saying that you can't be creative if you've got dyslexia, but it's not necessarily like an innate difference in people with dyslexia. There's no reliable evidence for it. Some studies have shown slightly enhanced creativity in dyslexia, but a very, I can't think of the word, comprehensive meta-analysis showed that the size of the effect, so the identified statistical effect of this difference, is really negligible. There's not really any difference. Any difference found is usually in studies with adults. And so we go back to then, could this be a consequence? So As I said, we often develop compensatory strategies if we're not very good at something. So this could be something to do with the strategies that have been developed by people who are struggling to read, or it could be a coping mechanism. So finding a niche, finding something that you're good at. And it goes back to the self-esteem thing and the frustration thing, but no evidence for it. Right. So things that you should know about dyslexia. We are nearing the end. I'm aware. I said I would be half an hour and it's 10 to. Children with dyslexia, they tend to have difficulty in mapping speech to written words. It's often comorbid with ADHD, dyscalculia, language disorder, dyspraxia, autism spectrum disorder. Early signs of dyslexia: less able to recognize rhyming patterns, so the cat sat on the mat, that sort of thing, not really getting that those are rhyming words. Difficulty in breaking words into different sounds, so thinking of something like pencil, being able to break that down into pen and sill, and using vague or inexact vocabulary when describing things. So this is access to the words. It's also, the observable characteristics of dyslexia do vary with age. At the earlier stages, it tends to be difficulties with decoding individual words. And then as reading demands increase, it's more about comprehension and fluency. And then in adulthood, you still do, adults with dyslexia do tend to still struggle with spelling and also written expression, organizing the presentation of information. And the difficulties with memory, attention, etc., do continue into adulthood. Interventions that we know are effective, though there's still work to be done to personalize them more, but teaching the links between letters and sounds and recognizing common words. So these areas of the brain that I talked about earlier. So the frontal lobes are sometimes increased activation in dyslexia. So the frontal lobes are working overtime to compensate for the deficits, the reduced activation in these two areas, in the language area and the visual recognition area. But after activation, after intervention, you do see greater activation in these two areas, in the language and visual recognition area, but not in the frontal lobes, which is why you continue to see beyond remediation the problems with working memory, organization, etc. Why it's important to understand these, and I promise I'm getting to the end. Early identification, one thing we do know is the earlier you can identify and therefore make reasonable adjustments and implement interventions, the better the outcomes for the child. Neuromyths, it's good to understand those because there are a lot of people out there who want to make money and selling things that they will tell you will help children with dyslexia read, and these can waste valuable resources, money, staff, and time. And it's important to understand the lifelong effects beyond remediation. Right, I have finished. Sorry, Erica, I told you I would be quick, but I have finished with 7 minutes to go.
Yet again, we had another successful webinar. We had a high number of attendees once again. So thank you, Rebecca.
No problem.
Got some messages saying how
my
well you explained, how clear you explained throughout the webinar. I thought of letting you know.
Oh, thank you. Thank you. That is good.
We have a few questions here. The first one is there any evidence that the age children start reading influences the deficits found in dyslexia and potential differences in the brain as a result?
Quite possibly. So you're saying is that the deficits that you found, so you've got a child with dyslexia, children with dyslexia, and the later they start reading, would that actually affect the brain, potential differences in their brain as a result? Well, this takes us back to the consequence cause thing, whether these brain differences are a result of familiarity or exposure to reading, or are they actually causing the difficulty? Neuroimaging, more recent neuroimaging evidence suggests that it is due to lack of exposure to reading. So in which case I would say to that question that quite possibly later reading results in in more brain differences, but I mean, I'm not a neuroscientist, so I'm reluctant to say too much on that, but there is research looking at that. That could possibly be the case.
Something very linked to this, which I'm going to ask here. Locally, we tend to wait for a child to be 7 years of age to diagnose either with dyspraxia or dyslexia. Is it too late? Is 7 years of age too late? Because we tend to start, the academics a bit early here locally. So is 7 years of age too late to diagnose dyslexia?
I don't know whether too late, because we have a lot of successful intervention studies that, that start when children are diagnosed, which is typically the age of 7. But that because of these broader deficits, it might be possible to identify children much younger, so in preschool. And I'm actually doing a study at the moment looking at early executive function and emerging literacy. And the very early findings are showing that the executive abilities, so this is about understanding future planning. So, if you imagine these are 3 to 5 year olds, so the limited future planning that they would have, it tends to be children who are poorer at future planning do have problems with this emerging literacy, which is like pointing to things in a book and asking what it is or saying the word. We've measured them on language as well, and it doesn't correlate to language. So it suggests that there's something very much about the executive deficits and the literacy. And if this is the case, it will help, because it will mean that we can diagnose children who are likely to go on to develop dyslexia before they even start to learn to read. So that would be a good thing.
Okay. So my concern is the next question. My concern is that once a child realizes that they are unable to keep up with their peers in reading, and at times use compensatory strategies such as resting on memory and pictures to recall information, such strategies become less viable as the student progresses in the years of education. Besides supporting a fragile self-esteem and the scheme of possibly feeling a failure or a second best, what issues would a child with dyslexia need support within counselling?
Ooh, I am not a counselling psychologist. But I mean, I think that you wouldn't have to be to see that there needs to be, it needs to be addressed in some way, that they should be given the support and the positive feedback and the understanding that, some people struggle with this and these compensatory strategies are okay, and alongside intervention, so they do eventually get up to speed with their peers. And then they'd be less likely to need these strategies that you've talked about, at least for reading, not for the other broader deficits. I would say that it's quite obvious that there should be some psychological support, but I'm not, in terms of the type of counselling, I wouldn't have a clue. I'm not a counsellor.
So with letter reversals, very often we find they come within a context of more grapheme phoneme correspondence difficulties, and that beyond a certain age are significant to note, don't you think?
Yes, I do. Yeah, I think I mentioned this very briefly in the talk, that if they continue to do this beyond the typical age, you might think, okay, so there is obviously a problem here with that grapheme phoneme correspondence. But what tends to happen is when children do it at the younger age, when everybody's doing it, so there are two issues. One is when, most children, not all children, but a lot of children do it. It doesn't mean that they're all at risk of dyslexia, but also that a child may never do this and still have dyslexia. Those are the things to note.
And our last question. So if a child can't make, no, there are more. So if a child can't make the sounds, how will they do the linking of letters to sounds?
If they can't make the sounds, so it's not so much that they can't make the sounds, it's that they can't map the sounds. So they don't, well, actually, that's not quite true. That they can make the sounds, but that there's more. I didn't get into this because it's quite a big area, but there is also evidence that children with dyslexia have issues with sound differentiation. So you know what I was saying earlier about d, 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 b, b, b. So if I make the sounds d, 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 and b, 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 you can hear that I'm doing D's and B's probably. But there is some evidence that children with dyslexia are more likely to have a problem with differentiating those sounds, in that it takes them longer to do so. So the rapidity with which those speech sounds are produced. And if you think about now while I'm speaking, I'm making so many different speech sounds, like so many different ones, and some are very, very similar, that it takes children with dyslexia find it very difficult to separate those different speech sounds. But that is a whole other area of research. So I wouldn't take that as absolutely definitely always the case with children with dyslexia, but it may be linked to the difficulty they have with linking it to the letter.
Okay, our last question. Can a sign of dyslexia be if one reads a word internally but says a different word verbally or whilst reading out loud? Same with numbers. You mentioned that those with dyslexia have difficulties accessing sounds that they know.
They have accessing the matching of the phoneme to the grapheme. Some children with dyslexia do. Others don't have that deficit. They have deficit with the visual recognition. So if what you've said, if one reads a word internally but says a different word verbally when reading outside, I don't know. I don't know much about. I'm sure that somebody has done that, but how would you measure a word somebody says internally without asking them? But then how do they tell you? I don't know.
Yes,
I don't know.
You can't measure
that. Don't know.
what they read internally. You wouldn't know.
So there was a question above. Can we observe dyslexia as a consequence of being taught opaque languages? More complexity, more dyslexia, more dyslexic. Well, more complexity, there are more diagnoses of dyslexia, yes, but the research into dyslexia as having these problems that we've talked about, the phoneme grapheme matching and the word recognition, they still exist in transparent languages and in non-alphabet languages. They just don't manifest as much or at all in the case of non-alphabet languages as dyslexia, because there's something innate where this deficit lies that is manifesting as reading because it impairs the abilities that we've talked about, but it doesn't mean it doesn't exist in other languages. It's just not dyslexia. The impairment exists, but it's not dyslexia because they don't have difficulty reading, if that makes sense.
Yes. Okay, we're done. James, Michelle, thank you, Rebecca, for today once again.
Thank you, Rebecca, for another interesting presentation, this time about dyslexia. We thank you for your contribution to this series of webinars. It's your second contribution, so we're really delighted to have you again with us. I would like to share my screen just to announce our fifth webinar, which will focus on ADHD. It will be next Tuesday, so at the same time. And this time we'll have Matthew Slocum. I think he's a PhD student. Erica, am I right?
So yes, he is, with the Center of Education and Neuroscience.
That's right.
Yes.
And his focus will be on ADHD. I've already shared the link to register, but we'll also share this link and the recording eventually on the Facebook page of the Faculty of Education. I thank again Rebecca, Erica, Michelle. I'm not sure whether you'd like to add anything before we
just a quick thank you, Rebecca. You managed to address a lot of queries that we all had about dyslexia, because it's either someone from our family or some student that we taught. We have encountered the situation firsthand, and what you described was very helpful, at least personally.
So
I'm very pleased to hear that. Thank you.
So thanks again, Rebecca. Thanks again, Michelle and Erica, and all the attendees we had today. Thanks again and have a nice evening.
Hi, good evening.